want to do is we want to have a comparison between the two elements that we studied before. One is one is L and one is C. In particular, a solenoid versus a parallel-plate capacitor. In the case of a parallel-plate capacitor, we not only studied its capacitance, we also realized that once we put some charge on it, it establishes an electric field, and that electric field stores energy. Okay, we call it electrostatic energy. Now, in the case of magnetic field, you have a solenoid and you drive a current through it. Okay, you drive a current through it, and it takes energy to establish a current because you're going to have to fight against the self-inductance of that solenoid. So the current will not jump abruptly to a certain value, but once you establish a current, you establish also a magnetic flux, a magnetic field. Does that field carry energy as well? Just like the electrostatic field. We suspect it will, right? Because of the symmetry between E and B. So we're going to study the energy aspect, okay, of inductors, and hopefully from that we'll be able to derive a formula for the magnetic energy density, just as how we used the parallel-plate capacitor to derive the expression for the electrostatic energy density. Okay, so let's see here. I have a solenoid. Okay, I have a solenoid in the circuit. I run a current through it. Initially, the current is equal to 0, and the final value of the current is I. In doing so, how much energy do I have to give to the inductor? Well, I have to drive this current with against the potential difference, which is epsilon L. Right? I have to drive it just like driving a car up hills. I do work against gravity, then I gain gravitational potential energy. Here, I have to drive an increasing current through a solenoid like that to have to overcome epsilon L. So the power that has to be expended in order to drive such a current through it is epsilon L times I. Okay? Now, epsilon L is L di dt. The magnitude, okay? The magnitude is L di dt. Multiply this by I. Right? This is the power that has to be expended in order to run a variable current through it. Suppose you start with a 0 current, end up with a final current I. What is the total amount of energy you have to expend? Well, that would be epsilon L I dt, right? Because this is just power, it's energy consumed per unit time, and that's the total amount of energy you have to spend from certain amount of time to final time, t. Okay? And let's see how much that is equal to. This side is equal to that side, so I can redo this calculation. I L di dt times dt, and then integrate 0 to t. Now, cross out the dt, you integrate over di instead, okay? This is L, which is a constant. 0 to the final value I di, right? That's 1/2 I squared, so this becomes 1/2 L I squared. So that tells us that in order to establish a current in an inductor, okay, from 0 current to a final value current I have to overcome this much energy. In other words, I have to do this much work. I have to feed this much energy into the inductor to establish such a current. And this current, of course, will produce a magnetic field, and that magnetic field has energy. How much energy does it have? This much energy. Okay, this much energy. So this expression has two important meanings. One is from an inductor's point of view. Okay, I know that once I establish a current through an inductor, this inductor has this much energy stored on it. And the other thing is, I can rewrite this I in terms of magnetic field in the system, in the interior of the inductor. And from that, I can express this in terms of magnetic energy density. Okay, so we are going to see how we can rewrite this expression, this I, in terms of magnetic field. And it's not easy to do it for general geometry, but we can do it for a simple case where this inductor is nothing but a solenoid. Okay, if it's a solenoid, for a solenoid, ideal long solenoid, L equals what? I know what that is. It's mu naught n squared, and then V, right? Remember that? V is the volume. Okay? Now, meanwhile, I would express I in terms of the magnetic field. Okay, the magnetic field. So what's the magnetic field equal to? Well, the magnetic field B is mu naught n I. Right? Okay, I can solve for I, which is B over mu naught n. Let me plug both of these into here. So the magnetic energy, okay, this in fact is the magnetic energy stored in the inductor once a current I runs through it. So UB, the magnetic energy, I should put a UB here as well. Okay, equals to 1/2 Li squared, and that is 1/2 mu naught n squared V times I squared. I is B over mu naught n squared. You see, n squared cancels. You're left with 1/2 mu naught. You're left with 1/2 mu naught B squared times the volume. Okay, this is the magnetic energy stored in the region of volume V. So what is the energy density? Energy per unit volume. That is lowercase u. Okay, small ub equals big UB over V, and that equals 1/2 mu naught B squared, right? 1/2 mu naught B squared. Does that expression come as a surprise? Well, it shouldn't. If you recall, the electrostatic energy density is 1/2 epsilon naught E squared. Now look at the symmetry between the two cases. We know there exist symmetries between E and B. 1/2 and 1/2, they both are here. And every time I see epsilon naught, I should replace it with 1/mu naught if you want to go to the magnetic case, right? We said that before. And E, of course, replaces B. So that's why these two expressions are totally symmetrical. In fact, we're going to study later a case where both the electromagnetic energy densities need to be considered if you have both an E field and B field in a case of electromagnetic waves. This is just one more piece of evidence that there exists high degrees of symmetry between electric field and the magnetic field. Now, the expression that we got for the magnetic energy density whenever there's a magnetic field present was obtained for such a special case of a solenoid. But I want to tell you that with enough math, we can show that this is not limited to the case of a solenoid. Anytime you have a magnetic field, B, there's always energy per unit volume. Even in a vacuum, you have this much magnetic energy per unit volume. Just like even though we found this expression using a special case of a parallel plate capacitor, the result is not limited to the case of just a parallel plate capacitor. Okay, this is valid for any electric field. You have this much electric energy density. So please make sure you understand this is a universal expression for the magnetic energy density. Now, as a byproduct, this result, the magnetic energy, also has gives us a new way to calculate the value of the self-inductance. Okay, so as an example, we're going to revisit the coax cable problem. How does one calculate the self-inductance of a coax cable using an energy approach? The idea is, suppose I know the magnetic energy density, U, I can find then the magnetic energy of the entire system, right? UB, by integrating. UB equals 1/2 Li squared, we just learned in the previous page. From that, we can find L, 2UB over I squared. So instead of calculating the magnetic flux, I can calculate the magnetic energy first, and then divide it by I squared times 2. I should get the same value for the self-inductance. Okay, now take a look at the case of coax cable. Okay, first of all, the magnetic energy density is 1/2 mu naught, actually 1/2 mu naught, and then B squared. Okay, so that's that. But as a function of R, okay, as a function of R, the magnetic field is mu naught I over 2 pi R, right? So let's consider, let's go back to this diagram here for the coax cable. Let's consider a region between the inner cylinder and outer shell. Okay, this region of length L. In this cylindrical region, there is a magnetic field, right? And let us look at a shell area of radius r and r plus dr, between r and r plus dr. Within that shell area, the magnetic energy density is uniform because we know the magnetic field is uniform. So we can integrate, we can find the magnetic energy within this shell of radius r and r plus dr by multiplying ub with what? The volume of the shell, right? And then we can add all the contributions up, all the shells up, to find the total magnetic energy between here and there. And then we're going to multiply 2 divided by I squared and see what happens. Okay, so let's do that. This is the magnetic energy density. Multiply this by the volume of the shell, which is 2 pi r circumference dr. 2 pi dr gives you what? 2 pi r dr. This is dr. Gives you this cross-sectional area. And then multiply by the height L. That gives you the volume of that shell. Multiply that volume of the shell by UB, you get the magnetic energy stored within this shell. So you get dUB equals small ub times dV. Okay, let me copy that ub here. It's 1 over 2 mu naught. In fact, let me clean things up a little bit. 1/2 mu naught squared over mu naught, so it's mu naught, then I squared over 4 pi squared r squared. And then multiply by dV, which is 2 pi r dr times L. Okay, let me then integrate UB, the magnetic energy stored between radius R, radius A and radius B for length L is equal to, I have to integrate over R, okay? So I'm going to integrate over R. I'm going to clean things up a little bit further. There's a 2 pi, there's a 4 pi squared, so overall you get 1 over 4 pi, considering that 2 here. I squared. There's an L, okay. And then what more do you have? There's R, there's 1 over R squared, so it's 1 over R dr, okay, from A to B, right, from A to B. So, what do we have? Mu naught I squared L over 4 pi, right? And the natural log of B over A. This is the total magnetic energy stored in the region between the inner cylinder outer shell from radius A to radius B and length L. Okay, times 2 over R squared over I squared. So L equals what? Take this expression times 2 over I squared. I squared is gone. Times 2, so this becomes 2 pi. Mu naught L 2 pi natural log B over A. You can move that L over here. You get the inductance per unit length. So you can compare with the expression we got before. See, here's our energy approach, and here is our previous approach by calculating the flux directly. You see, exactly the same result. Okay, so you can use either method, either by calculating the magnetic energy or calculating the magnetic flux directly. Either way, you can find the self-inductance. Okay, I want to emphasize on one thing. Self-inductance is not the only way for inductance to be present. Inductance basically means that if you have a changing current in a circuit, it can cause an induced EMF. Okay, but that changing current, could belong to another element. It may not belong to the element itself. If the current running in the element itself changes, causing an inductance, okay, causing an induced EMF, then we call it self-inductance. But there is also something called mutual inductance. A simple example, suppose I've got 2 loops, okay, loop 1, loop 2. Now there's a current I1 running in loop 1, there's a current I2 running in loop 2. Now suppose they are close by, so that any magnetic field produced by one of them will be felt by the other. And let's say, for whatever reason, there is a changing current running through the first loop. So I1 changes over time. Okay. Now I1 produces a magnetic field which also goes through the second loop because they're close by. Okay, so you get a magnetic flux caused by I1, which goes through both the first and the second loop, like this, right? Now, if I1 changes over time, then that magnetic flux changes. The flux going through the second loop also changes, right? And then there will be an induced EMF. Now, that induced EMF is not because I2 changes, rather it's because I1 changes. So, it is possible to produce an induced EMF in an element due to the current change in somebody else, okay, a nearby element, right? It is not caused by your own current change, it's caused by somebody else's current changing over time. And then we say that there is a mutual inductance between these two elements close by to each other. A changing current in one element can cause an induced EMF in the other element, and vice versa. Okay, to put it down in an equation, there can be epsilon 2, which is induced EMF in the second loop, caused by a changing current in the first loop. Okay, that is di1 dt, not di2 dt. Of course, it is not equality yet. I have to put a constant. It's not L. L is self-inductance, right? This is I1, not I2, so I'm going to put M. M stands for mutual inductance. Put a negative sign indicating the direction of epsilon 2 is always against the change in I1. Okay, I put 1 to 2 here. This is the mutual inductance caused by loop 1 on loop 2. Similarly, the change in current I2 in the second loop can also cause an induced EMF in the first loop. So I have epsilon 1 equals negative M21 di2 dt. This is how the two loops can influence one another. It's called mutual inductance. Okay, it can be shown generally, even though we're not going to do it here, that M12 always equals M21, no matter what the shape and size of each loop. They don't have to have identical shape. They can, any shape. You put them nearby. If one can influence the other influences it back with exactly the same inductance. Okay, this can be shown with general energy considerations without reference to any particular geometry, but I'm just presenting here as a result without any further proof. This is the concept of mutual inductance, but we're still going to focus primarily on self-inductance. So I'm introducing this only as a conceptual approach at this point. Now, one of the interesting applications of mutual inductance is the so-called inductance charging. Usually when we charge something, they charge a battery. What we usually do is just use a plug, and there are metal parts, right? The battery has two metallic terminals in contact with the metallic terminals of a charger. But the problem with that is that if the battery that you're charging, you expect it to be wet, okay? Then the water that you use may be contaminated with minerals, whatever. It becomes a conductor, and that can cause a short circuit in the system, and that can be dangerous. A particular example would be a cordless toothbrush. Okay, now it is, as you know, it's often wet, and if you ever use a cordless toothbrush, you can see that there is no open exposed metal parts. Okay, here is the base. Here is the bottom part of a electric toothbrush. It's got a little bit cavity inside like this, but it's all encased in a piece of plastic. Okay, there is no conducting parts, and then here is the base. Here's the charger. Okay, there's a wire connected to power supply, and the charger has something protruding out, but it's also encased totally in plastic. There is no metal exposed to the air, so that's safer. And yet, you put this toothbrush on this charging base, even though everything in contact is only plastic, it starts to charge. Okay, so you wonder how that works, right? Well, the magic behind it is inductance charging. Inside the base, the plastic covered base, there is a coil, like a solenoid. Okay, there's a solenoid like this. Now, you run a current through it, right? This is AC current. So naturally, there will be a variable magnetic flux, okay, which of course can go through plastic, even though you cannot see it. Now, what's inside the bottom part of a toothbrush? Well, there's also a magnetic, also a solenoid. It's like that. Okay, so you see, basically, as the current changes, there will be an induced EMF due to the red wire, due to the current change in the red wire. Okay, it will be picked up by the green solenoid, right? The green solenoid will then, there will be a current going through it, and that's powered by the induced EMF. That current is the charging current. Okay, so even though there is no direct metallic connection, for safety reasons, you can still charge. It is an example of inductance charging. Okay, in the next part of the lecture, we're going to study more examples of how to put these three elements R, L, and C together. We already studied RC circuits before. We already studied RL, an earlier part. We're now going to study the LC circuit. Okay, you know, whenever you put a resistor in a circuit, no matter what the current direction is, this way or that way, no matter how the current changes, as long as you drive a current through a resistor, from energy point of view, electrical energy is always turned into heat. Okay, it always dissipates, turned into heat. And yet, when you drive a current through an inductor, or when you charge a capacitor, things are different. There is no thermal energy involved, right? There is no heat dissipated. Rather, when you do work against a capacitor or an inductor, you get some reward, and the reward is you're building electric energy and magnetic energy into it. Okay, so if we consider a case where there is no resistor, okay, there is only an inductor plus a capacitor, then there is no mechanism to turn electromagnetic energy into heat, right? So what happens if you have a certain amount of initial electromagnetic energy in an LC circuit and yet no resistor in it? Will this electromagnetic energy somehow magically disappear? Well, you suspect it probably wouldn't, because there's nothing that can turn the electromagnetic energy into heat, right? That means the current, once established, will be there. It will not diminish because of thermal energy loss. That's our intuition. Is that really the case? Well, we're going to see in our next part, the so-called LC circuit. And later on, we're going to put the resistor back into the system, because in the real world, there's always some resistance in any circuit. So we consider what's called LRC circuit. And we will learn that a quick and easy way, an intelligent way of discussing problems like LC and LRC is to compare this situation with the simple harmonic motion system that we studied, a mechanical analogy in Physics 1B. And you can see that there is a great deal of similarity between the two cases.